All right, so this brief lecture on vectors starts off with a bit of a review from what we've covered in summer assignment, and then extends that knowledge into actually numerically looking at how do we combine vectors. This video lesson is good for not only the AP Physics 1 class, but the AP Physics C class. There's one section that AP 1 does not need to concern themselves with, so I will tell you what slides to skip, but otherwise it goes along with your notes. All right, so if you need additional resources, the physics classroom is an excellent resource. The link is posted right here, and I've also posted it on Schoology. So if you go to the electronic copy of the notes, you can click on this link quickly, but you can find it on Schoology more easily. But I have also, at the very end of this video lesson, I take you through a quick tour of this link so that you can kind of find what you need as far as extra practice. So a resultant vector. A resultant vector is something that results when you take the sum of two or more vectors together. So the vector sum of two or more vectors equals the resultant. So vocab word here. So if we talk about the resultant, we know we want to think that, okay, we're taking the vector combination of two or more vectors. So if three vectors added together, does the order in which they are added matter? No, it does not matter. So I can have vector A plus vector B plus vector C, that should be a plus sign there, and that is equivalent to adding it C plus B plus A. Does not matter which order you add them in. How does vector subtraction differ from vector addition? It really doesn't. Essentially, if we want to subtract two vectors, that is equivalent to just adding them. But then if we remember, we take the 180-degree flip of the second vector. So that's the 180-degree flip. So again, just quick review of work that we've talked about before. All right, so we wanted to discuss two graphical methods of adding vectors together. We have covered the tip to tail method, and I also want to kind of mention the parallelogram method. Both methods are fine for conceptually adding vectors together. So tip to tail method, as we've discussed before, I draw the first vector, so I'm looking for the summation of vector E plus vector D, and then I place the tail of vector E at the tip of vector D and continue drawing. So that's the start of E, and then I'm just trying to make that kind of parallel there. So that's vector E, that's vector D, and then the resultant, you draw the resultant, you start it where you started your first vector, and you finish it where you have finished your second vector. So that would be what I'm going to call vector R, the resultant vector. So that's what we've kind of learned before. The parallelogram method is a little bit different, and I'm just going to basically recreate this diagram right here and just draw vector D and then vector E. So this way I have both vectors starting in the same place. It's basically this drawing right over here. And then I complete the parallelogram. So I'm going to make a parallel side to E. So there's my parallel side to E, and then a parallel side to D. And then the resultant starts there at where all the other vectors started. So they're bundled together. And then I draw it to the opposite corner. So that is going to be my resultant there. So either way, you can do a parallelogram method or a tip to tail method. This obviously is not going to work if you have more than two vectors. Tip to tail method is kind of like the preferred method to use, but typically we are only dealing with two vectors anyway. All right, so far we have just done scale models using arrows and combining them, which is what we have demonstrated up here. Now we want to do a more quantitative treatment of these vectors. So in order to do this, we have to choose a relative coordinate system. So what kind of coordinate systems are we going to choose from? We could have an X, Y, and possibly a Z coordinate system. And this is what we call a rectangular coordinate system. Rectangular. We could actually have a horizontal and vertical coordinate system. Again, that could kind of mirror the X, Y, Z, but we could call it horizontal and vertical. And then we could take this X, Y, Z coordinate system and we can actually tilt it at an angle. And this usually comes up when we're looking at objects moving down a ramp. We might tilt our coordinate system to kind of mirror the angle of the ramp itself. So that comes up a lot with ramp problems. And then the last coordinate system are radial coordinate system or rotational coordinate system, where we're looking at circular motion or rotational motion. So we'll run into those too towards the end of the year. All right, so once we get into this quantitative analysis, which means we're going to use number, the first thing we want to choose, as we mentioned, was the relevant coordinate system. And then any vector that's relative to that coordinate system is going to be broken down into the components that are parallel to that system, such that when they are added together using tip-to-tail or parallelogram method, they return the original vector. Now, this sounds like really confusing, and I get that. Like, what did you just say? I don't understand this, but I think it's going to make more sense when we actually start looking at various examples and using the proper vocabulary. So, relevant vocabulary that I want you guys to kind of understand is that we're going to deal with components and we're going to deal with a resultant. And basically, if I wanted to kind of simplify it, if I look at a triangle, because we're going to do mostly like 90-degree kind of stuff here. So if I have a triangle like that, the legs of the triangle are going to be the components. The resultant is going to be the hypotenuse of the triangle. This is essentially, basically what we're going to be doing in a nutshell. All right, so more vocabulary that we need to deal with here, and actually talking about breaking vectors down into their components, and then we're going to reassemble them. So this reassembly is what happens when we're actually doing the vector addition piece that will come a little bit later in this lecture. So let's just look at an example. So we have vector A here that is lying along an XY coordinate system. So we're going to choose our coordinate system to be kind of the standard XY system. So vector A, this notation right here stands for vector A. A with a subscript X and A with a subscript Y, these are the vector components of A. So along the XY coordinate system. So if we look at our diagram right here, I'll switch colors here, okay? This is vector A here. If I do tip-to-tail addition, this is going to be A sub X, and this vector right here is going to be A sub Y. So this is what I meant on that previous slide that sounded super complicated, that components are basically, if I were to add them together, would result in the original vector, which is the resultant. So we have this vector right here, and I can break it down into the X and the Y components such that, I'm going to switch colors again here, that vector A is equal to A sub X plus A sub Y. So these are two vectors that I'm combining together that returns the original vector. This is the resultant. These are the components. All right, so this absolute value over the vector sign, or just looking at vector A, typically is talking about the magnitude of A, which means the size of it, the numerical value that's associated with the length of that hypotenuse. And then A sub X without the little vector symbol on top, these are also talking about the magnitude. So if I'm doing a little bit of SOHCAHTOA or trigonometry here, A sub X is going to be equal to the hypotenuse times the cosine of the angle theta. And I'm going to label angle theta right here in my diagram. And then A sub Y, magnitude of that, is the magnitude of vector A times the sine of the angle. And then the direction of these vectors are going to be along the X and Y coordinate system. All right, so this slide is for the C class only, AP Physics C class only. So AP Physics 1, if you are listening, you can skip this slide. All right, IJK notation, which is important for AP Physics C because sometimes we run into it. So as I mentioned before, A sub x, if I want to look at the magnitude of the vector, is A times the cosine theta, and A sub y is equal to the magnitude of the hypotenuse times the sine of the angle, and this is just SOHCAHTOA stuff. But if I want to write this as a vector equation, this is just magnitude right here. If I want to add in the direction piece and give that component, typically the angles are expressed in terms of IJK notation, where I, and it has a little hat symbol over it, represents a unit vector in the direction or along the direction of the x-axis. And then J and this little thing caret here is called a hat, and this is similar, but it's along the y-axis. And then K hat is a unit vector along the z-axis. So it gives us direction to these components. So if I wanted to write this vector A in terms of its magnitude and direction, I would write A cosine theta, this is along my x-axis direction, I hat. So this piece gives magnitude, and this little piece gives direction. And a unit vector means it just has a value of 1. So it doesn't do anything to the magnitude of this piece of it. It just gives it some direction. And then I would add to it the y component of my A vector, which would be A sine theta times J hat. And then this would be a vector equation. All right, so let's go through a quick example of breaking a vector into its components. So we have a vector here, and we'll call this vector B here, and it's like down and to the left, or 25 degrees below the negative x-axis is the direction of it. And I want to break it into its components. So to visualize, I'm going to draw just kind of a dotted line here to represent the components of B. So this would be B in the x direction, and this component vector would be the component of B in the y direction. So these are my little vector quantities there. And now I want to actually solve for it numerically. So we're basically going to use SOHCAHTOA here and solve for these vector equations. So pause the video and give it a try. All right, so let's do an example problem of breaking a vector into its components. So a couple things to remember. So if you have a vector that points to the left or downwards, that's typically going to be our negative sign. So in XYZ coordinate system, that would represent negative. You need to put that negative sign in manually. So the first thing that I'm going to do is take this vector 7 that is down to the left, and I'm going to draw the components. And I'm going to draw them as dotted lines here just to kind of show that these are components of vector B. So this is vector B right here. And then I'll draw the component in the other way. So this is the vector in the y direction, and this is the vector in the x direction. So we're going to kind of split here a little bit, and I'm going to kind of talk to AP1 over here, and I'll talk to AP Physics C over here, just to make this a little bit simpler. So now this is going to be for AP Physics C. If I want to solve for this component B sub x, I'm going to do SOHCAHTOA. So I'm going to take 7 times the cosine of 25 degrees, and then I have to give it a little bit of direction. This is along the x-axis, of the negative x-axis, so I'm going to manually put that negative sign in, and then I'm going to give it an I hat, and that's going to give it the direction. Similarly, for B sub y, it's also aimed downward, so I have to put that negative sign in manually, and that's going to be a sine of 25 degrees, and then J hat. Now, AP Physics 1, we're just going to solve for the magnitude of B sub x. We're not going to worry about direction so much, and we're going to put in the negative 7 times the cosine of 25 degrees, and then the magnitude of by. So just don't worry about this J hat stuff. Minus 7 times the sine of 25 degrees. So if we plug that all into our calculator, this is going to be equal to minus 6.3 3, and this one will be equal to minus 3.0. And this would be a j hat, and this would be an I hat. And as far as AP Physics 1 is concerned, you're just kind of looking at the magnitudes of these vectors, and you're kind of thinking about the direction just with the negative signs there, 3.0. So be careful. Here's a little caveat. Don't forget that vectors, all vectors, are going to have magnitude and direction. So with AP Physics C, we tend to be a little more explicit with the IJK notation. For AP Physics 1, we can be a little bit more loose and just kind of note that the X is going to be the X direction, and then you have your direction with the negative sign there. So just be careful in making sure that when you draw these component vectors here, that you draw them as little tip-to-tail additions or parallelogram additions, and not just making triangles, because the arrowheads will remind you about the direction. A couple things that we'll be needing to do with vectors throughout the course of the year. So if I multiply a vector by a scalar quantity, all that does is multiply the magnitude. It does not change the direction at all. So there's no change in direction. So I'll do a quick example of that here. So if this is my vector A right here, then vector 2A would just be 2 times as long, but in the same direction. So this angle here would still be the same, would not change. Dot products and scalar cross products, we are going to deal with these later in the year, but basically dot product is a special kind of multiplication which results in a scalar quantity. And a cross product is another special way of multiplying vectors that results in a vector quantity. But I will table more details for this when we get into those units. All right, so this is the money piece. This is the thing that we are going to be doing quite a bit, and that is the adding the vectors quantitatively. So what I'm about to do and discuss right now, if you want more practice with this, you want to go to that AP Physics classroom site. And again, at the end of this video, I take you through how to get to that site and what might be good places to look for to get some extra practice. So let's say we have two vectors, and they can be any kinds of vectors. These could be force vectors, these could be velocity vectors, they could be acceleration vectors, but I just need to add them together. And this is what we're going to be doing a lot of. So let's say vector D is 5 units to the east and vector E is 7 units, but it's 30 degrees south of east. So south means below and east means the positive x-axis. So that's just another way of kind of describing how we're making that angular measurement relative to something. So if I want to look at d sub x, and I'm just doing magnitudes here, that's just 5. Whatever the units are, we're just going to call it 5. The y component of that, well, there isn't a y component to that, so its y component is just going to be 0. Now, E sub x is the one that we have to worry about and do the SOHCAHTOA trig with. So E sub x, if I look at the x component of it, that's going to involve the cosine of the angle. So that is going to be 7, which is my hypotenuse, times the cosine of 30 degrees. So I'll just do another quick kind of reminder of SOHCAHTOA. So you have SOHCAHTOA. And in doing right angle trigonometry, if this is my angle, this is the hypotenuse, this is the adjacent side, and this is the opposite side. So if this is something that you don't recall from your trig in previous math classes, this is something, just reach out to me and we'll go over and review this. But I'm not going to take a ton of time in class to do this because there's kind of an expectation that you're up to speed on this. But if you want a little bit of review with me, absolutely reach out. All right, so 7 times the cosine of 30 degrees, that is about 6.1 units, whatever that is. And E sub y, in this case, this is being pointed downward. So remember, this is my E sub y, and this is my E sub x. I drew in my components to that. This one is going to be negative, so I need to make sure that I put that negative sign in conceptually. And then I'm going to take 7 times the sine of 30 degrees, and that is going to be minus 3.5 units. So now we want to add the components in the same direction. So I'm going to add d sub x and d sub y, and then I'm going to add e sub x and e sub y, and these are going to give me my component of my resultant. I'm going to call it f in this case, in the y direction. And when I add, I'm sorry, when I add the y components together, that's going to give me f sub y. And when I add the x components together, that's going to give me my x component of my resultant vector. So f sub x is equal to e sub x plus d sub x, just the x components. So that's going to be 6.1 plus 5. That's going to be 11.5, and that's in the positive x direction. And then f sub y is going to be 0 minus 3.5. So f sub y is just going to be minus 3.5. So I can construct what my resultant vector looks like. It's going to be 11 units in the positive x direction. So this is f sub x. And then my y component is going to be negative 3.5 units downward. So that would be our minus 3.5, and that's going to be f sub y. So my resultant, my final vector f, which is what I want to find, is this hypotenuse right there. So I'm going to write down this is 11.1. So the magnitude of f, I'm just going to do Pythagorean theorem. So the magnitude of f is going to equal 11.1 squared plus minus 3.5 squared, square root of that whole thing. I've done the Pythagorean theorem here, and if I plug this into my calculator, I'm going to get a magnitude of 11.6. For AP Physics C people, you could also write the vector f in IJK notation, and you can just say 11.1 I hat minus 3.5 j hat, and that would be the vector f. So either one of this is going to give you magnitude and direction. This would be the magnitude of vector f. But now if we want to find the direction or the angle measure of vector f, we have to solve for this angle right in here. And I'll kind of get a different color here, this angle theta right there. So to do that, we have an opposite and adjacent side. We even have the hypotenuse side as well, but I usually like to use the ones that are given. So I'll typically will use the tangent of the angle is going to be equal to the opposite over the adjacent, which is going to be the 3.5. Again, here we're just solving for this angle. We're kind of ignoring the negative signs now. We're just going to solve for theta, just like you would do in a math class. 3.5 over 11.1. So theta is equal to the inverse tangent of 3.5 divided by 11.1, and that is equal to 17.5 degrees, and this is below the positive x-axis. And equally correct is you could solve for this angle right here and say that it's the complement of it, which would be like 72.5. To the right of the negative y-axis. So those are also equivalent results. So this is the big thing. We need to be able to add two vectors together that are not necessarily right along our coordinate system. All right, so the next page is just a quick video that shows you the link to the physics classroom if you want some more practice of adding vectors together.
All right, if you flip to the next page, there's a practice problem that I'd like you guys to try on your own. Please solve for the components, the magnitude, and then finally the direction. Use the example that we just did to help you through it, and then we'll check answers when we come back together again. If you want more resources, go to the next slide and I'll show you, there's an online link to something on the physics classroom that can help you if you'd like additional practice with this.
Okay, so that link at the top of the note pages, and that's also on Schoology, takes you to the physics classroom, which takes you through a tutorial on vectors and for motion and forces in 2-dimension. We're going to focus right now just on the vector part of it, but this is also a good link for what we're going to lead into very soon, which is projectile motion. And basically A, B, C are what we have done kind of conceptually, adding vectors together just by drawing pictures of them using tip-to-tail addition. But this one starts to get into more of the detail of using trig and SOHCAHTOA. So if I click on this component addition, which is what we're going to be doing a lot of this year, there's a lot of information and a lot of review about combining vectors and drawing the resultants. And there's a lot of practice problems here, and I'm scrolling through it quickly. because it definitely goes through a lot of the detail there, the different components, breaking it down into the X and Y component, just as we kind of talked about. So if you want to see more of this, this is a great place, and it has excellent examples and more practice. So if you keep going, and I know this is a long page and you don't have to go through all of it, there are interactive sims that you can play with, and I think the vector in addition interactive is really good, but you can actually do some practice here with combining vectors mathematically, and then you can check your answer at the bottom, and there are several examples right here at the bottom of the page in combining 1, 2, and 3 vectors. I would limit yourself for AP Physics 1, just 2 vectors here, and then kind of doing this kind of example. This one's a little bit more advanced, but you certainly can look at that. And then doing a little bit more of a word problem involving combining the vectors, which again, kind of review of what we've done over the summer assignment, but definitely getting into more of the mathematics of it and looking at vectors that are at angles to each other.